Do you know when are you expecting us to finish this?
Oh yeah, homework 3. How about we make it do a week from today?
Great.
Any objections?
Nope.
No? Okay. All right, let's do that. Yeah.
3C here, do you mean for that side to be a beta?
Yeah. Yeah. I believe so. Yeah. Yeah, I found a typo.
Oh.
That's good, but bad.
All those poor students who have come before us.
Wait a minute.
Yeah, if you want to read it.
No, that is correct. Yeah,
So-
that's side. Yeah, tangent psi is AY over AX.
But yeah, I get that, it's just that, you know, what you get is,
Okay. All right, there's no typo. Excellent.
No.
Okay. Any other questions? No? Okay. So let's see. Last time we talked about uses of quarter wave plates, so we looked at optical isolators. We said something about polarizing beam splitters, and then when you use a quarter wave plate with a polarizing beam splitter, you have a nice way of getting light to go in and then kind of come out with the opposite polarization state, and then you can do something in between. Whether that was a phase shifter or we talked about what, CD, DVD, Blu-ray pickups, etc. Q switch for laser. Okay, so today what we want to do is keep on with our polarization and just some useful things, including how to create in the polarization state with a polarizer and a quarter wave plate, and therefore how to analyze any polarization state with a quarter wave plate and a polarizer. But first, let's do the following example.
So I have a better question. So where did form bioreferencing like come into play with what we're talking about?
Oh, just something for you to be aware of.
Oh,
Yeah, that if you don't have the right birefringent material, you can actually make it.
okay.
Yeah. And so, for example, in the mid-infrared, far infrared, there are no good birefringent materials. So that's why we made our own,
Okay.
doing the subwavelength ratings.
All right.
Yeah. Okay, so let's say that we have a rotated, arbitrary wave plate, and we put that between cross polarizers. So in other words, we start off with a polarizer in the X direction and end with a polarizer in the Y direction. And then in between, we stick a wave plate with some arbitrary retardance, gamma. And what we want to know is what is the transmitted power? So we already know what the transmitted polarization state is, right? What would be? What's that? Yeah, linearly polarized in Y. Can't be anything else because there's a polarizer right there. So we know what the polarization state is. We want to know how much power we get out given what we put in. So the first thing we need to do is set up the system matrix, Jones matrix. And so we have a polarizer in the X direction. And then we rotate an angle beta. And then we have a wave plate. And then we rotate an angle minus beta. And then we have a polarizer in the Y direction. So if we write these things down, polarizer in the y direction is 0, 0, 0, 1. And then this thing right here, I think we've done it before, haven't we? So I'm going to do the usual, my usual shorthand. C is cosine of beta, S is sine of beta. And now A super plus or minus is going to be my shorthand for e to the plus or minus j gamma over 2. And if we use those shorthands, shorthand notation, then this arbitrary wave plate rotated becomes c squared a minus plus s squared a plus, and then we have cs a minus minus a plus, and then we've got cs a minus minus a plus, and over here we've got s squared a minus plus c squared a plus. And then we have the polarizer for the x direction, 1, 0, 0, 0. And if we do the matrix multiplies, we end up with just one element. And it's going to be the element in the lower left-hand corner, because that's the element that controls x into y polarization. So we have 0, 0, and then cs a minus minus a plus 0. So that's our system matrix. And then the cs, that's cosine of beta, sine of beta. And then we can use a trig identity and call that 1/2 of sine of 2 beta. And then the a minus minus a plus, that's just e to the minus j gamma over 2 minus e to the plus j gamma over 2, which is minus 2j times sine of gamma over 2. So we can rewrite this matrix as 0, and then we have minus j sine gamma over 2 sine 2 beta 0, 0. So that's our system matrix. And now let's say that we start off with a Jones vector over here that is 45-degree linearly polarized light. Then the output Jones vector over here is just going to be the system matrix times the input Jones vector. So we have 0, 0, 0, and then I'll just call this, I don't know, C. So C is just this thing over here. Oh no, we already used C. Let's call it,
Is that field or 2?
1 over root 2, sorry.
No, I meant that 2, the bottom one.
Here, where?
Right there. The right hand side, negative 2j sine of.
Sine of gamma over 2. Yeah, gamma over 2, yeah. Yep. Okay, and then we have 1 over root 2, 1, 1. And so when we multiply it out, what we end up with is 1 over root 2, and substitute in for the g, which is just this thing over here. So we have minus j sine of 2 beta sine of gamma over 2.
What did we say that the G was again?
It's just so I don't have to write that out.
Ah, gotcha.
You can see I'm kind of lazy with my notation, or we could say streamlined, efficient.
You write readable code.
Oh, okay, well, yes, yes, we'll say that.
Yes.
Carlos?
What is this Jones vector, the one line? What is that representing?
This is, yeah, what does that represent?
The input.
Input,
Yeah, that's your JN.
oh, so we're saying if we put a wave that's polarized in that,
Uh-huh, and what polarization state is that?
one that's linear.
Linear what?
Linear to 45.
Linear 45 degrees. So we're coming in at 45 degrees. And then already, we know we're gonna lose the Y component because of that, right? And then the X component's gonna get manipulated by this thing, and then we'll lose all of it except for the Y component.
So we have to put that.
So basically what we did here was we took those matrix manipulations and summarized it to S. Is that right? Is that what the S stands for?
Which, oh, yeah, this, uh-huh.
Okay. Oh, there
Yeah,
it is.
yeah. Yeah, that's right. Okay, so we're all with it? Yeah, Karen?
To me, it's like we use all these examples for a specific case that the angle is 45 degree, right? So is it common, this angle 45 degree, because
We're just choosing it arbitrarily. We could choose linear polarization in the X direction. We could choose in the Y direction, but that gives us a trivial result. No light will go through. We could choose circularly polarized light here.
so if you choose, let's say 40 degree, and then the wave plate still can do the changing polarization from linear to circular?
Well, the wave plate will change it from linear. It'll be linear in X here after the X polarizer. And then it's going to change it to something, we don't know what. I forgot to say this angle is beta, because that's some angle beta, and this is some retardance gamma, whatever, just arbitrary.
The only way we get circular out of that is if the input to the wave plate is 45.
Yeah, that's my question. So if the input is not 45, we cannot be sure that the output from wave plate is circular polarized, right?
That's correct, it will not be circular. It'll be some elliptical state, yeah,
Okay.
that's exactly right. Perfect. Okay, so then here we could calculate the transmission, and the transmission is what? Yeah, of what to what?
Input to output.
Input what to output what?
Power.
Yeah, or irradiance. So we could write it as output irradiance over input irradiance. And when we work it out, what we end up with is 1/2 sine squared of 2 times beta sine squared of gamma over 2. So that is the transmission of the system. And now notice that if we have a fixed retardance, meaning we have some wave plate here, whatever it is, and then we just rotate it, meaning that we look as a function of beta what the transmission is. So we're just changing beta, then what will it look like? Yeah, well, it'll be a sine squared dependence. And a sine squared dependence looks like this, right? And what's the amplitude of that?
Sine squared and gamma over 2.
Uh-huh. Yeah, 1/2 sine squared gamma over 2. And what's the period? What's that? So if it was just sine of beta, the period would be 2 pi, right? Sine squared of beta, the period is pi. Sine squared of 2 beta,
Pi over beta.
pi halves. right? Because if that's pi halves, then this is pi, sine squared of pi is 0. So that gives us the first 0 there, right? And so this would be pi, 3 halves pi, etc. So this maxes at pi over 4. Okay, so great. We've messed around with math. What does that mean?
Means by changing beta alone, you can change the transition drop.
Yeah, absolutely. Mhm.
So
Yeah.
So it's like for changing the color, you can change either phase retardation or the angle beta.
Yeah, right. So looking at that specifically, if I had some wave plate and I didn't know what the retardation was, I could always take it, stick it between crossed polarizers, come in with linear polarization at 45 degrees, just rotate this thing, measure as a function of beta what the transmission is, and the amplitude is directly related to gamma, therefore I can measure gamma. So if you have an unknown wave plate you pull off the shelf, no big deal. You can easily measure gamma. Okay, so that's nice. On the other hand, if we fix beta, then what happens as a function of gamma?
Same thing, but you have 1/2 sine squared 2 beta as the max.
Yeah, so same sort of thing. But this is 1/2 sine squared 2 beta. And then what's our period here?
Pi?
Yeah, well, 2 pi,
2 pi.
right? Because we take
Oh,
2
yeah,
pi,
yeah.
stick it in there, that's pi, sine squared of pi, 0. Okay. But, you know, in practical terms, that's not as interesting. Generally, you know what angle you set the wave plate at. Okay, great. So, now we've learned how to measure the retardance of a wave plate. Now, let's figure out how to create any arbitrary polarization state using just a wave plate, quarter wave plate that is, and a polarizer. Okay, so what we have is a system where we have a linear polarizer at some angle, call it beta prime, and we have a quarter wave plate at some angle beta, and we control beta and beta prime. We can set them to whatever we want. And we come in with some polarization state over here. Doesn't really matter what it is, because this is going to turn it into linear polarized light at angle beta prime, right? So if we came in with, say, circular polarization here, then it doesn't matter what angle beta prime is, we'd always get the same amplitude coming through this, right? Okay, so we're not going to worry too much about that. That's kind of easy. But what we want is this output polarization. We want it to be any state possible to have. In other words, we want to use this as an arbitrary polarization generator. So we want to be able to make any polarization state we wish. So the question is, how do we do that? And to get at how we do it, the first thing we need to do is the following. Let's just draw some arbitrary elliptical polarization state. And it could be clockwise or it could be counterclockwise polarized. But it's just some arbitrary state. And, you know, it could be circular if, here's A and B, if A and B were equal. Could be linear if B was 0. And this is at some orientation angle phi, right? And then it has some ellipticity, which is plus or minus B over A. And so in the XY frame, then we have components AX, AY, and a phase difference delta. But what I want to focus on is in the X prime, so this is the XY coordinate frame. What I want to focus on is the X prime, Y prime coordinate frame. What is AX prime?
Cosine.
Just A, all right? And so AY prime, just B. Okay, and then what's delta?
Maybe it's 7.
Not the same as
Delta
this.
Y. It's going to be, depending on the orientation, it's going to be positive or negative pi over 2.
Yes, that is it. So this is going to be, maybe I'll prime it just to indicate we're in the X prime, Y prime frame. It's going to be plus or minus pi halves. And that's the key fact. How do we know it's going to be plus or minus pi halves? Well, we know that tangent of 2 times the orientation angle is equal to 2 times AX AY over AX squared minus AY squared. This is in the XY coordinate frame. Cosine of delta, well, this is just in any coordinate frame. And if we're in the X prime, Y prime frame, then phi is equal to 0, right? So if phi is equal to 0, tangent of 2 phi is equal to 0. So we have that 0 is equal to 2 AX AY over AX squared minus AY squared in the primed frame, cosine of delta in the prime frame. So maybe I'll put little primes on here just to remind ourselves. But clearly the only way for this to be true is if delta prime is plus or minus pi halves. Because delta prime, whatever, is always between minus pi and plus pi. Therefore, that is always true in the X prime, Y prime frame. Okay, so that, like I say, that is the key fact. Yeah.
Remind me again what delta stands for?
It's the phase difference between the Y and the X components. Yeah. I'm glad you asked, because that's important. Okay, so in the X prime, Y prime frame, delta prime here is the phase difference between the Y prime component and the X prime component. Okay, So, that being our key fact, what does a quarter wave plate do? It gives us a phase shift of what? Pi halves for light propagating in the fast axis relative to light propagating in the slow axis. So our quarter wave plate always gives us a phase shift of pi halves. Well, pi halves. So we can use our quarter wave plate to get that phase shift. And all we have to do then is figure out how do we get the right amount of A and B in order to get the polarization state we want. Okay, so let's see how that works. So basically what we do is we set the slow axis, which is at an angle beta, we set it equal to the orientation angle of the ellipse we want to make. Pardon?
This is the polarizer.
The wave plate. So the fast and slow axis. The slow axis, we set it at the angle, the orientation angle of the ellipse we want, polarization ellipse we want to make. So that gives us the orientation angle phi for the polarization ellipse. Because whatever comes through the fast axis is, by definition, going to be leading whatever comes through the slow axis by pi halves. So we can get that plus or minus pi halves here. We'll talk about the minus in a moment. So then the question is, how do we get this ellipticity from the polarizer? So for example, let me just draw a polarization state here, just so we have something concrete to talk about. Okay, and then remember we drew a box around this? Okay, and this distance on the box is B, this distance on the box is A. And then if I draw a line to this corner, what's that angle? Theta, which is the ellipticity angle. Perfect. So the tangent of the ellipticity angle is B over A. Right? Okay. So if I set the polarizer angle, beta prime, to be the orientation angle plus the ellipticity angle, then in the x prime, y prime frame, or in other words, in the slow fast axis frame, I'm going to get a component A and a component B, and B is going to be phase shifted by pi halves relative to A. Okay, so by changing this ellipticity angle here, meaning changing the angle of the polarizer, I can get any polarization state that is, what is that? That's going to be clockwise.
It's trippy.
Still a 50-50 shot.
Yeah? Okay, so we're basically concentrating on plus pi halves right now.
So A is leading.
Well, B will be leading A,
B's leading.
because this component travels on the fast axis, this one on the
that's
slow
right, that's
axis.
right.
Gotcha.
Yes. Yep, I'm glad you mentioned that.
So what is B prime in our actual setup?
B prime.
Oh.
Beta prime?
That, so if we set that equal to that, oh, okay.
Yeah, so we're setting the polarizer angle beta prime equal to the angle, or our orientation angle of the ellipse we're trying to generate, plus the ellipticity angle.
And so we want that so that when it's coming to the quarter wave plate, it's at the right electricity angle.
Yeah, it's at the right ellipticity angle relative to the slow and fast axes.
Oh, and then it.
Yeah, and then pi halves phase shift, boom, we've got the polarization state we want.
Would we subtract theta if we wanted the opposite circular?
So if we want the opposite, then that's the ellipticity angle here at minus theta.
So the first one is.
First one gives us,
counterclockwise?
first one is clockwise,
Oh, okay.
because, going back to the finger method, you know, fast axis, slow axis, quarter wave plate, we get a pi halves phase shift. As this hits my nose, I'm going to see this first, then that, so that means I'm rotating clockwise. And over here, if I go to minus theta, so this would be beta prime is equal to phi minus theta. Then in that case, I've got, you know, this much field in the slow axis, and then this much in the fast axis. And so this is going to lead, and so it hits my nose first, but it's going to be rotating to the fast axis, which is counterclockwise. So do you see how it works?
Yeah. Does that mean that phi isn't necessarily needed unless you're maximizing the power through the system?
Well, phi is, it's just,
Like if
for the polarization state you're trying to create, you can characterize it with phi and theta. And so phi, it just comes back to what polarization state you're trying to make, and therefore what orientation angle does it have. If you want an orientation angle that's 0, well, life is really simple. You know, set the slow axis to 0, and then make beta prime just equal to the ellipticity angle.
Yeah, that's what I was basically
That's it.
saying.
Yep. That's right.
It's the relative difference that's the important part.
Yeah, so this, or alternatively that's what sets the ellipticity. And then the angle of the slow axis, that's what sets the orientation angle. Okay, so what do you take away from this little discussion?
Someone thought about that too.
This picture should become natural for you.
This is kind of like the minimum way to do any polarization you want.
Yeah, that's right. Exactly. So if you have a, you know, light from a laser beam, or from a light from a laser, and let's say that light starts off linearly polarized. Then basically you want to take the laser and rotate it so that the linear polarization state is at beta prime, and then take your slow axis, put it at beta to get whatever polarization is you're trying to achieve. Now, what if you can't take your laser and rotate it? And so you have a linear state coming out, and you need to rotate the linear state. What do you do? Yeah, you could, and then you're going to throw away power.
You could do a halfway plate.
Halfway plate. So whenever you need to rotate a linear state and not lose any power, except for reflected power, just use a halfway plate. So if you start off with a linearly polarized source, then you could use a halfway plate and a quarter wave plate and make any polarization state using these principles. Yeah.
Why would you use a halfway plate? It seems like you could always rotate the quarter wave plate with a polarizer in a system you're building.
Well, the assumption is you're trying to make some arbitrary polarization state, which means that you have to be able to have an arbitrary orientation angle phi. Now, if you know what that orientation angle is, then you can set up your system with the proper rotation in it when you make it, so that your quarter wave plate and your source are appropriately rotated. Yeah.
If you do this with a half-wave plate, would you orient it the same as the linear polarizer?
Well, so if you did it with a halfway plate, you'd be coming in here with some polarization state. I don't know, let's say it's vertical. That your laser, when you put it on the table, polarization state is just coming out vertical. And you need to rotate it over here. Well, then you just stick a halfway plate in here, and here's the initial vertical, here's the slow axis of the wave plate. The effect of the halfway plate is to flip this about the slow axis.
So you just want to make that match what you want from the linear polarizer?
Yeah, so then you want this to be at that angle beta prime.
Okay, so you do halfway between wherever you start and beta prime.
Exactly.
Okay.
That's exactly right. Okay. So quarter wave plates are pretty useful. Yeah.
When, say, designing an optical system, like, say, in those old CD drives or DVD drives, how large is manufacturing tolerances compared to, say, the quarter wave plate?
Depends. So fortunately, you're starting off with a laser source, which is relatively monochromatic. So for a laser diode, the line width might be, I don't know, say a nanometer. And then that means your quarter wave plate's going to work really well across that entire spectrum because it's so narrow. So then the tolerance is basically just getting your quarter wave plate to be close enough at the center wavelength of the laser diode. And then it's good. And that's not too bad because that's just the thickness of the quarter wave plate, given whatever material you're using.
And that's not bad because lasers are very coherent, so they can tolerate
Very narrow line width,
narrow. Oh, yeah,
which is the same thing that you said, but just saying it
yeah.
a different way. Yeah. Yeah.
So if you start with a linear polarization and you're using the half-wave plate, could you make do without the linear polarizer?
Yeah,
Okay.
exactly. So you're starting off, you're using the fact that your source is generating a linear state.
And you're just going to rotate it with the half-wave plate to whatever the quarter wave plate is.
Exactly, to in essence, the linear state that this would have generated.
Yeah. Okay.
Yes, that's exactly right.
Oh, okay. So that's the same thing. I see.
Yes.
So you align it as if the linear polarizer were there, but then you don't use the linear polarizer.
Precisely.
Okay, that makes sense.
That's exactly right. Okay, so looking at this, what is the key fact that enables all this? Oh yeah, those
The
things too.
anisotropic material.
It's this. It's that fact. That when you're in the reference frame of the, that's natural to the ellipse of the polarization state, when you're in that reference frame, the phase shift between the y and the x-axis is plus or minus pi halves. That is what makes it all work. That's the key thing to remember. Okay. All right, so that's how you generate an arbitrary polarization state. So how do you measure an arbitrary polarization state? Yeah. You have some polarization state you don't know what it is, but you've got a quarter wave plate and you've got a polarizer, and you want to use those two to measure that unknown polarization state.
Orthogonal linears and then something else to get the circular nature.
Well, you basically just do this in reverse. Because you have the light come in, take your quarter wave plate, rotate it until you get a linear state out, and take your linear polarizer and rotate it at 90 degrees to that linear state, and now you get no line through, right?
So
That makes sense.
So by measuring the angle that you've got your quarter wave plate at, and the angle at which your linear polarizer is set to block all the light, then you can directly figure out what the orientation angle is and what the ellipticity angle is. Therefore, you know the unknown polarization state.
So you use the quarter wave plate to make it linear, right?
Mm-hmm.
But once you make it linear, you don't know that it's linear. So you
That's
just wait
right.
until it's zero.
Well, so what you do is you take your quarter wave plate, just put it some rotation angle, whatever it is. Take your linear polarizer and just rotate it.
until it's zero.
Well, rotate it and see whether you ever get to zero. If you don't get to zero, then you know you don't have your quarter wave plate exactly lined up with the axes of the polarization loops. So then you change your quarter wave plate a little bit, rotate the polarizer all the way around, and you keep doing that until your polarizer nulls out the light.
Is there more than one solution or no? Is there just one?
Well, there's one solution of the polarizer angle relative to the quarter wave plate angle. But there are two quarter wave plate angles you could be at and make the measurement. Okay, so measuring an arbitrary polarization state, no big deal, just quarter wave plate followed by linear polarizer. Okay. All right, and it turns out that when you're measuring the optical properties of thin film, which we'll talk about when we talk about ellipsometry, it's all about measuring a polarization state. So this is one way to do it. Although an ellipsometer uses it differently, that we're going to talk about. Okay, so now another point, and this gets back to a quarter wave plate, its wavelength dependence. We haven't made a big deal of this yet, but now it's time to. So the retardance is 2 pi over lambda naught, n slow minus n fast, times the thickness L of the wave plate. And looking at this, we see that the retardance is proportional to 1 over the wavelength. So therefore, if we get a quarter wave plate at, say, 633 nanometers, it's not going to be a quarter wave plate at 514 nanometers. So you normally buy quarter wave plates and half wave plates, for that matter, for a particular wavelength. Okay, so if we have what's called a zero order quarter wave plate, then the retardance is equal to pi halves. And in that case, we can solve for the thickness, and the thickness is going to be lambda naught over 4, 1 over n slow minus n fast. And if we have quartz, then n slow minus n fast is pretty small, and the bottom line is that L is equal to 858 nanometers. That's an awfully thin piece of quartz.
For what kind of light?
Oh, sorry, this is calcite. So, if I do it for quartz, then quartz has an even smaller difference. 1 over smaller means bigger, right? And so in that case, L, the thickness, is equal to 16.4 microns. Even that, there's no way. I mean, how'd you like to handle that? You'll break it every time.
But you could do multiples of that, can't you?
Yes. Yes, absolutely. So we could do a multiple order quarter wave plate, in which case we're doing m plus 1/2 times pi. So yes, you're absolutely right. just go for the, 100th order.
It doesn't
And,
break when you handle it.
yeah, so now you got something nice and thick enough that's robust, so you don't break it.
Is this for the quarter wave plate? Okay.
Yes, for the quarter wave plate.
That's M, and then is that plus 1/2?
Yeah, plus
Okay.
1/2. Okay. So, but the problem is that this is still proportional to wavelength. So it goes as M plus 1/2, 1 over wavelength. So that becomes the wavelength dependence. In other words, if I were to plot the retardance as a function of wavelength, then let's say that this is pi over 2 for our quarter wave plate. Then the 0 order quarter wave plate is going to have a dependence like this. It's 1 over lambda. The multiple order quarter wave plate is going to have a dependence like this. It's M plus 1/2 over lambda, or M plus 1/2 times pi, rather. So we've got the M multiplying the 1 over lambda. So if we have 100 for M, then what that means is we have 100 times greater wavelength sensitivity. And that's horrible. So you really, really, really want a 0 order quarter wave plate. And you want it so that you have as much wavelength tolerance as it's possible to get. But then it's too thin. So you can never handle it. So the way around the problem is to construct a quarter wave plate in the following way. Take a plate of whatever, calcite, quartz, and let's say we stick the c-axis in this direction, and we have some thickness that's easy to handle, say L2, and then glue it to another plate of thickness L1, but put the c-axis orthogonal to the other plate. And so what you want then is that L2 minus L1 is equal to lambda naught over 4, 1 over n slow minus n fast. And now basically what you're doing is essentially making, a 100 order quarter wave plate and a 99 order quarter wave plate, and subtracting one from the other to get a 0 order quarter wave plate.
What is the c-axis again?
That's the, well, it depends on whether we have a negative or a positive uniaxial crystal.
If it's positive uniaxial, it's going to be a slow axis.
Yeah.
If it's negative, it's going to be the axis.
Right.
Did you say this is the same material each plate?
Same material, just 90-degree orthogonal c-axes, different thicknesses, so you hit this condition and now you've got a 0 order quarter wave plate. So whenever you buy a 0 order quarter wave plate, that's always what you're buying. So when you look up in a catalog quarter wave plates, make sure you don't buy a multiple order quarter wave plate unless you know you're only going to use it for your application that's really narrow line. Instead, buy one of those, but then you're going to pay more money.
What are those called?
It's a 0 order quarter wave plate. Yeah, because it's the only way you can make one. Yeah.
Do they do these where it's just 2 lengths, or one basically kind of reverses the sensitivity of the other, or do they do several, like lots and lots?
Just 2.
Just 2.
Mm-hmm.
Okay.
Sorry, I was writing down something, but what was the problem with the multiple order quarter wave plate?
This M is multiplying the 1 over lambda naught dependence. So you get a much greater variation in retardance when you shift off the wavelength. Yeah. Okay. So any questions? All right. Now, let's do our next topic.
Martin, could
Yeah.
we use that greater wavelength dependence to like isolate the wavelength we actually want? Even in, like, a narrow
Yeah,
source or something?
yeah, you could. Yeah. It turns out there are other ways to do it that
Better ways?
work better, but you're absolutely right. In principle, you could do that. Yeah, that'd be kind of a fun thing to show. Okay, so this Babinets Soleil compensator, its purpose is to give you arbitrary phase retardation for arbitrary wavelengths.
Wow.
Yeah, so it's basically a variable wave plate. So if you need a quarter wave plate for say 590 nanometers, no big deal. You can set this thing to do it. And then let's say you turn around and now you need a half wave plate for 633 nanometers, no big deal. You could take this out, put the other setup, change the settings, and now you've got what you need. So it's really a useful element, but it's really expensive. But nonetheless, just so you know how it works, you start off with a block of birefringent material, and say the c-axis is in this direction. And then on top of it, what you do is put a wedge of the same material, but put the c-axis in the orthogonal direction. But there's a problem, and that is that, this thing is varying in thickness, so, you'd have to move along here to change this. That's not very convenient. So instead, what you do is take an identical wedge, flip it upside down, and stick it right on top. And then be able to move this, so keep the c-axis in this direction, and then take this wedge and make it movable. So now you've got a constant thickness here, so it doesn't matter within some region where you come through. If you want to change the retardation, just move that wedge, and you change the thickness. And so now, arbitrary retardants or arbitrary wavelength, you're all set.
That's all that's mechanical like that.
Just mechanical.
Why do they cost so much?
What's that?
So why do they cost so much?
Just because, usually this will be calcite, and calcite is expensive because you have to mine it, and you have to get, a piece that's big enough to have the optical aperture be clear and not have defects.
And then I suppose that the micrometer precision or nanometer precision that you need for the machines.
Yeah, it's high precision linear stage. So it's pricey. I haven't priced them in probably 15 plus years, but way back when, $2,000, $3,000, $4,000, something like that.
You got one then?
No, I did in Alabama, but when I came to BYU, I had made sure that our department hired a guy who I knew could take my place. So, I set this up, I think 2 years before I left. And so he was there, but the problem was he got assigned to go through all my stuff to make sure I didn't take anything with me here that they wanted to keep there that was paid for with state money. Anything I bought with federal money, I could bring here, which is where some of the clean room stuff came from when I brought it. And so he was an optics guy and very savvy, and so he knew which state purchase stuff ought to stay, and this was one of those state purchase things. But if he had not identified as such, then I would have been perfectly free to bring it with me here. Therefore, I do not have it. It's okay. All right. So, now what we want to do is see how you use one of these things in a way to determine an arbitrary polarization state. And this gets back to homework problem number 3. Okay, so we want to determine polarization state with a Babinets-Soleil compensator and a fixed polarizer. So let's say we have over here our XY axis system, we just draw some arbitrary elliptical polarization state, and so it has an orientation angle phi, and it has an ellipticity of whatever. And so the question is, if I take my Babinets-Soleil compensator and I rotate the slow axis to be at some angle beta here, and then I change the retardance, can I find some combination of angles for the rotation angle and retardance here, such that if I take a polarizer and I put it in the y direction, I just fix it so it doesn't move. Can I get two settings here for some state so that no light goes through that? And then can I determine what the state is here under those conditions? So if we set up the system matrix, then basically what we have going into the compensator that we need to rotate by an angle beta. And then we have the compensator which has some retardance gamma, whatever we end up setting it to. And then we rotate back to our laboratory reference frame by minus beta. And then we have a polarizer in the y direction. Okay, so if we write down the matrices, this is 0, 0, 0, 1, and then we already wrote down the matrix for this thing, I think it was beginning of class. So we have c squared a minus plus s squared a plus, then we have cs a minus minus a plus, cs a minus minus a plus, and then s squared a minus plus c squared a plus. So that's our system matrix. And then if we multiply that out, what we end up with is 0, cs a minus minus a plus, and then s squared a minus plus c squared a plus, and then a 0 up there. So that's our system matrix. Okay, and then we have some instant polarization state here. We can write this Jones vector for an arbitrary state as cosine of psi, sine of psi, e to the j delta. So that's our input Jones vector. And basically what we want is our system matrix multiplied by that Jones vector. We want no light to come out. So let's multiply this thing. So if we substitute in for the system matrix, substitute in for the Jones matrix, and do the multiplication, what we end up with is a 0 for the x component, because we have a polarizer here at the end, oriented in y. And then we end up with cs a minus minus a plus cosine of psi plus quantity Yeah, question? S squared A minus plus C squared A plus times sine of psi e to the j delta. So that's what we get just multiplying out the right-hand side. And so what we must have in order for this all to work is that this term has to be equal to 0, right? So we have 0 is equal to CS, A minus, minus, A plus, cosine of psi, plus S squared A minus, plus C squared A plus, sine of psi, e to the j delta. So that has to be true. Okay, so at this point, and this is where what homework 3 is to go from this and show that it leads to the following two expressions. Cotangent of delta is equal to tangent of gamma over 2 times cosine of 2 beta, and tangent of psi is equal to sine of 2 beta times tangent of gamma over 2 divided by the square root of 1 plus the quantity tangent gamma over 2 times cosine of 2 beta quantity squared. And that, of course, is going to be AY over AX. Okay, so your job in problem number 3 is basically to show this. How do you get two equations or two unknowns from one equation?
You put imaginary unknown parts of it equal to 0.
Yeah. This is in general complex, so you really have two equations. You have a real part has to be 0, imaginary part has to be 0. Therefore, you can solve for 2 parameters. Okay, so that's homework problem 3. Yeah.
So at the beginning, when I asked if you meant beta instead of psi for homework number 3,
Mm-hmm.
do you still mean psi?
Yes.
So
Yes. Yeah, so I mean, going from the first equation to the bottom two, it's just algebra and trig, right? Okay. So, any questions before we move on? And by the way, this setup that we just looked at, in ellipsometry, that's normally what you do to determine the polarization state. But we'll talk about the details later. Okay, so now we do next topic. And the next topic is something called adiabatic following. And let's talk about liquid crystals. So a liquid crystal is a material where the molecule is, there are different shapes, but let's just consider a cigar-shaped molecule. So if we have some liquid crystal material, we've got these cigar-shaped molecules, any physical system always wants to minimize its energy. And so for a particular temperature range, the way liquid crystal minimizes its energy is it stacks up like this. So the cigar-shaped molecules all get kind of lined up. And let's say that we have here the z-axis, x-axis, y-axis. Okay, so if we propagate in the z direction, this material looks birefringent because we can resolve a polarization state into a component that's parallel with the long axis of the molecule, and a state that's orthogonal to the long axis. Those two states will see different refractive indices, therefore birefringent material. Okay, so what we do is we take the liquid crystal material and we stick it between two, say, sheets of glass, and we treat these sheets of glass so that the molecules that are immediately adjacent to the glass all line up in one direction. How do you do that? Well, you can do it chemically, but usually the way it's done is, you've seen a paint roller. Presumably you probably painted a room and had to use a paint roller. Okay, so what you do is go down to the hardware store, buy a paint roller, stick it on a motor spindle so it spins, take your piece of glass, and just let that spin on it for 5 seconds maybe. Pull it out, and now you have some very tiny nanogrooves in the orientation of the fibers of the roller, the direction you're going. Put liquid crystal on that, and the liquid crystal molecules are going to line up their long direction in the direction that you just scraped up your piece of glass. Of course, you can't see the scrapes, they're so tiny. So treat 2 pieces of glass that way, stick it in your roller, put a drop of liquid crystal on, sandwich it, voila, you have that.
Do you need to treat both sides or both glass?
Yes. Mm-hmm. Yep. Yep. And so now what you've got is a wave plate. It's birefringent material. Great. If instead of the glass, let's say you put some indium tin oxide, thin film, so this is ITO. So you have some ITO on there, and it's really the ITO that's getting the little nanogrooves in it. Great. Okay, what if now you take a voltage and apply it across the ITO? And this separation here, let's say, is maybe 3 to 4 microns thick. That's pretty thin. So you put a voltage on across the ITO. What happens? Well, yeah, you get a field. Exactly. You got a field, and these things have little dipole moments. So they want to rotate and line up with the field. And now what do you have? What are the optical properties of that? Yeah, it looks isotropic because this polarization state and that polarization state, they see the same thing. So you've just taken your wave plate and you've turned it into a non-wave plate. And that's always how a liquid crystal display works. But we're missing one piece of the puzzle here. And that is, what happens in reality is that you take well, actually, let's do this. The Jones plate for a wave plate just looks like e to the j gamma over 2, minus gamma over 2, 0, 0, e to the j gamma over 2, right? Okay, so let's say that you take your 2 pieces of glass that you've rubbed this way. Let's say you take the top piece and you twist it. So you rotate it. In fact, rotate it 90 degrees. What's the liquid crystal going to do?
Change polarization.
Well, it's going to twist with it because the liquid crystal down here is pinned in this direction. If I rotate this one 90 degrees, the liquid crystal at that surface is pinned at 90 degrees compared to the first surface. So what happens in here is the molecules just smoothly rotate. They just twist. And when you make a liquid crystal display, that's actually what you do. Is you take the two plates and you twist them by 90 degrees. When you do that, it changes this Jones matrix. And let's say the twist angle is, well, let's just call it beta. So if we twist by beta, then, and if the birefringence is really big compared to beta, which in a liquid crystal it is, because the fast and slow axes, or NE and NO, are really big. It's like 0.1, which is huge. So when I do that twist, birefringence is huge compared to the 90-degree twist. So what happens then is this is the Jones matrix. And the interesting thing is that guy. So beta is 90 degrees. This is a 90-degree rotation. So if I lined up my polarization, say, let's say I twisted this 90 degrees, I lined up my polarization this way, I'd be aligned with one of the axes of the wave plate. And if I'm aligned with one of the axes of the wave plate, I only see one of these. I don't see the other one. So this has no effect. So all I see is that. And so my polarization then rotates 90 degrees, if beta is 90 degrees.
So you get on and off then.
Well, so with no electric field applied, then I've got my pneumatic liquid crystal, my liquid crystal molecules smoothly changing, rotating 90 degrees as I go through the stack, through the film. And what that means is my polarization state is going to rotate 90 degrees. So if I have a polarizer here like this and a polarizer like that, and I rotate 90 degrees, light will go straight on through. Now if I apply a voltage, I screw everything up. Because these cigar-shaped molecules stand up on end. And now my polarization state does not rotate. It goes straight through, gets blocked by that exit polarizer. Now I don't have any light going through. Now my pixel is off. That's how it works.
So it requires a voltage to be off.
Yes.
That's why the screens are clear when they're turned off, and then you turn them on, the black lines that form the text are bigger.
Mm-hmm. Yep, that's how they work. Then you want a color display? Well, just take every third pixel and put a green filter on it, red filter, blue filter, voila, now you have a color display.
So how do you address like individual pixels? Isn't it just like one big sheet of crystal?
So on one side, it's just one sheet. On the other side, it's actually a whole bunch of electrodes.
Oh, so like a transistor set for each.
Yeah. You know, or, yeah, and then you actually, if it's a polysilicon device, then you actually have these polysilicon transistors at every pixel. You know, another way to play the game would be to have lines this way and lines this way, and then do a matrix addressing. But that's kind of slow. So usually it's a polysilicon layer with ITO electrodes, and then the polysilicon is such that you can electrically address each of the pixels, and then you get this rotation.
How can you affect the brightness going through?
What's that?
How do you affect the brightness going through?
It's the backlight, right?
Well, it's how much voltage you put on and how much you disrupt this.
Okay. So the more you disrupt it, the blacker it will be.
Yeah. Yeah, there's a type of liquid crystal that has very fast response time. In that, then you can pulse width modulate it. Because, you know, you basically have it doing this so fast your eye can't tell. And so, you know, maybe you have it on 10% of the time, so now you've got 10% grayscale. And maybe you got it on 90% of the time, now you have 90% grayscale. But a normal twisted pneumatic liquid crystal, which is what most displays are made out of, the response times are kind of slow, you know, maybe single-digit millisecond, maybe two-digit millisecond. So, so in that case, you can't do the dithering. You have to just disrupt it with a voltage that's not fully on or fully off, and it's nonlinear. So you have to compensate for that in your drive scheme.
So where's the polarizer in this?
There'd be a polarizer here and a polarizer here.
Okay, so there's like glued on top of the glass.
Yeah, so MoxTech, yeah, and they're just, single polarizers for each side. So MoxTech in Orem, they actually make polarizers, wire grid polarizers, for these type of displays for projection systems. And the wire grid polarizers are fantastic because you can get really high extinction ratios, which means your black are really black. So when you go to the theater, then, it's a good chance you've got a MoxTech wire grid polarizer on the projector.
That's not for LCD projectors, right? Because they also
What?
have DLP projectors, they use LCD too.
No, not at
Yeah,
all.
that's actually the mirror.
That's a different
Yeah,
thing.
okay.
Yeah.
So for LCD projectors.
Yes, only for us.
So not at Cineplex.
Yes, exactly. That's right. Yeah, it used to be, you'd see LCD